How can you ensure your CAE solution is keeping up with the latest simulation technology? Welcome to today's webinar, Real FEA Made Easy. Let me start out by thanking you for your time today. We hope that you find the information that we are about to share beneficial for you and for your team. The question of the day is, how can you ensure your CAE solution is keeping up with the latest simulation technology? Hi, I'm Yvonne Wiedemann of CamLogic, and I'd like to spend the next 40 minutes or so showing you a way to protect your investment in 3D while getting a boost in productivity at the same time. First, I'd like to recognize Coach Yachts in France for supplying an image of one of their products, a luxury yacht. This design was completely modeled in solid edge and analyzed with Femap with NX Nastran. Let's start by familiarizing everyone with CamLogic. CamLogic has been in the CAD CAM CAE space for over 35 years. The company was established 16 years ago, initially focused on CAM, servicing mainly the tool and die shops in the local area, and is now servicing 5 states in the Midwest area. As the market has evolved, CamLogic has evolved. Interestingly, working our way backward from manufacturing back to the conception of the idea or design. Because we started at the end of the process and worked our way to the beginning, CamLogic has the fundamental knowledge of what has to be done to assure that each step of the process will result in a product that will actually work or fit into the surrounding phases of development. CamLogic has chosen to represent software and tools that enable our customers to fulfill the full cycle of product development. We consider ourselves integrators and partners for our customers, not just resellers. CamLogic employs the three-legged stool strategy. We partner with Siemens, offering the completely integrated Siemens portfolio for design, machining, analysis, and data storage and retrieval. We partner with 3D Systems for 3D printing and rapid prototyping, and Romer and Creaform for 3D scanning for inspection and quality assurance. Now that you've heard a bit about CamLogic, let's discuss Femap and CAE. If you are looking to learn more about Femap's powerful modeling functionality, this is the webinar for you. Today we'll take a look at some of Femap's powerful modeling functionality and see how it can be used to export a CAD model, fix problematic geometry, and prepare the model for subsequent modeling. Does this sound familiar? The most common problems aired by companies still tied to legacy Unix-based CAE pre- and post-processors sound something like this. There's a lack of Windows integration in both look and feel. These older platforms are aging in appearance and don't work with Windows very well, which in turn affects productivity. In some cases, development of these products have been sidelined by the developing company and are noticeably falling behind through lack of new functionality and working methods. Even though development of these products may have slowed, lack of investment in the product from the developers has not brought any cost reductions to the end users. All of these problems result in poor customer responsiveness. How can you ensure your CAE solution is keeping up with the latest simulation technology? By introducing a modern simulation solution into the design cycle, you can design to a more complex customer requirement through more advanced modeling and analysis functionality. With an up-to-date CAE solution, you can employ the latest simulation technology to more accurately represent not only the design itself, but also the operating environment in which it has to function. In this presentation, we'll see how Femap can deliver these capabilities and see the benefits with industry analyst validation and customer case studies as backup. Femap packages powerful modeling functionality within efficient workflows and a modern Windows-native UI for maximum productivity. Additionally, Femap can help you prepare more advanced and complex designs for simulation. Let's examine how. Increasing design complexity puts greater demands on simulation and exacerbates the typical problems, such as accessing CAD data or dealing with overly complex or poorly defined CAD geometry that impede early implementation of simulation in the design cycle. Also important is the ability to accurately and efficiently represent the physical behavior of the actual design through FE modeling representations, which depart from slavish use of the solid model, requiring more creative modeling techniques. Using these techniques with representative models of complex designs require proficient display controls to maintain productivity and ease of use. Customization is also important to allow interaction with other programs and to automate repetitive processes. Femap is a high-performance, finite element analysis modeling with Windows-native ease of use. Femap originated as a program used in the demanding aerospace industry with CAE professionals, but with its familiar Windows look and feel, it is easy enough for any CAE experienced user to run. Femap is CAD independent, allowing you to import CAD geometry from a wide variety of sources. Femap is also solver independent, but does have a high level of Nastran integration and can be purchased bundled with NX Nastran. When engineers need to get real results accurately and competently, they use Femap. The usability of a product is directly linked to the productivity of the users of said product. How quickly users can learn how to use the product and the relearning involved for infrequent users. Besides productivity, also impacted is the cost of training to learn the product. The more difficult the product is to use, the higher the training overhead. Advanced modeling techniques and analysis methods require in-depth model definition and setup, and to position advanced features in an easy-to-use interface is a challenge. Femap has been designed specifically as a Windows-native application, and as such offers a user interface in the familiar Windows style that promotes usability and efficiency. As well as being easy to use, learning to use Femap is also easy. And a reduced learning curve means reduced training overheads, which also makes the product easy to pick up and use for infrequent or intermittent usage. One of the key features of Femap is the ease of use, which is important for productivity and also from the point of view of learning the product. Key to the usability of Femap is the user interface. Windows native and designed to intuitively and efficiently display the detailed functionality necessary in a product capable of solving complex engineering problems. The user interface has recently evolved to include new features like the model info tree view and data table that effectively remove many layers and allow easy and direct access to the modeling data. As Femap evolves, some of these features have increased in importance too. For example, the model info tree is now a main vehicle that allows access to new functionality as it is coded into Femap. The model info tree also offers a powerful way of uncovering functionality in an intuitive manner, allowing users access to the underlying modeling data. These additions to the Femap user interface add variety to methods of working, or workflows in Femap, but without ever taking anything away. So all of the original menus remain in place as new methods of interacting with Femap and accessing the underlying data appear, such as new panes in the user interface and new icon bars. Also, New icons have been added to various dialog boxes that allow workflow branching. This means that not everything has to be created sequentially and in a strict order. If a point is reached where other data is required before proceeding, these icons will allow the work process to branch sideways, create the required definitions, and then continue without having to backtrack. So Femap packs powerful functionality into a user interface that is intuitive and easy to use and learn. This makes its users as productive as possible. Now let's take a look at Cad Access and see why this is important and review some of the main issues. The transfer of CAD data is desirable because it allows the CAD model to be reused for analysis purposes. However, the translation of the CAD model to the analysis environment is often fraught with problems. The problems can include a lack of support for the particular CAD data type or CAD system, or perhaps support doesn't extend to the latest version of that CAD system. There may also be limitations with geometry type support. For example, surfaces might be read in, but solids just might not. To overcome problems that obstruct data transfer, you often have to seek an alternative method to translate the model if possible, or resort to manually rebuilding the model in the analysis system. This, of course, can be very time-consuming and can end up delaying the whole design process. Flexibility of data flow is key to a standalone, independent program like Femap. Femap can leverage the modeling data that already exists in your current CAD system, whichever it is, and use it as a starting point to create the simulation model. Femap is CAD neutral and can access CAD data from just about any source and supports all major commercial CAD programs and CAD formats, and is kept up to date with the latest CAD product versions. The Femap modeling engine is based upon the Parasolid modeling kernel, which is the same that is used by SolidWorks and Solid Edge. Femap and Solid Edge are fully associative via the PLM XML pipeline, which allows direct transfer of parts and assemblies. Per Vincent's quote here, using Femap and Solid Edge has reduced design errors and rework, helping SAFT power systems speed up their time to market. One of the biggest impediments to the creation of a finite element model from a CAD model is bad geometry, whether it is inherent from the CAD model or introduced during import. From the CAD modeling perspective, the appearance of the model is often the only consideration. So it doesn't matter if it contains thin sliver surfaces or very short curves. But from the FE perspective, however, these small features or discontinuities can disrupt subsequent meshing operations and make it very difficult to create a good finite element model. Some FE modelers may lose small model features completely during import, and there may be no indication that some detail has been missed. This makes it very difficult for you to ensure that the model integrity has not been compromised. Troublesome geometry, slivers, gaps, short edges, is one of the main obstacles that has to be overcome in the creation of a finite element model. Sliver surfaces, for example, lead to badly shaped elements being created at the time of meshing. Even finding where these problematic entities reside can be a major task. This is where Femap's locator on the meshing toolbox comes into play. It is a dialog that you can use to control the search parameters and locate all of the troublesome curves and surfaces quickly and easily. Having located the problematic geometry entities, there are a number of tools available in Femap to make corrections and allow an accurate, well-shaped mesh to be created. Two of these tools available in the meshing toolbox are combined composite curves that will join up separate curves together, and combined boundary surfaces, which similarly can be used to merge adjoining surfaces. Using these tools, it's easy to overcome or eradicate small curves and surfaces by merging them to adjoining entities and produce a smoother, more regular geometry model that is ready for meshing. Other aspects of geometry handling include the ability to remove unnecessary features like small holes, fillets, and chamfers from the geometry model, again to help create a better mesh. Using Femap's meshing toolbox, these unnecessary features can be suppressed manually, giving you the ability to select those features that you wish to remove, or automatically to suppress all features smaller than a specified tolerance. Other tools available in Femap to help modify geometry prior to mesh creation include geometry splitters, which can be used to split large surfaces into smaller ones to help align the geometry and create surfaces that can be map meshed, which is a means by which regular quadrilateral surfaces elements are created. There's offset curves, which can create map meshable regions around complex geometry that comprises multiple curves. There's washer, which uses offset curves to create map meshable regions around holes, which are typical stress razors and where you would usually want a very good regular mesh for accuracy. And finally, pad, which creates the surface geometry surrounding a hole into 4 map meshable regions. Let's now look at the importance of modeling tools and see why some of the more simplistic approaches to FE modeling are not always appropriate. Accurate representation of real-world structures requires efficient finite element modeling techniques that stretch beyond the application of simplistic static analysis of solid parts. Finite element analysis most often come down to a simple balance of accuracy versus model size. Yet there are many modeling techniques that can be employed to reduce the size of the finite element model without compromising accuracy. With the advent of fast solid model meshers, it has become very easy to fill up a solid geometry model with tetrahedral elements. This leads to the creation of very large and unwieldy finite element models that require huge computer resources to run. Examples of geometry that is really unsuited for solid modeling are thin-walled type structures, for example, an airplane or ship-type structure, or frame structures such as a crane. Also, while static analysis creates certain computer resources, if it is desired to take the same FE model and perform a more advanced type of analysis, such a dynamic response, then the computer resources required increases dramatically. Another issue that arises through the adoption of some finite element modeling approaches is visualization, particularly for plate and beam top models. You are able to view the model with plates and beams appearing fully represented with model setup, and verification becomes easier to complete. NX Nastran offers a couple of solvers, sparse and iterative, which can be used depending on the type of FE model created. The Iterative Solver is very efficient at running large solid models for static analysis and is much faster than the sparse solver for this type of model and analysis. The sparse solver can be used to solve more general FE models that contain element types other than solids. However, if you're eventually looking to perform more advanced types of analysis, then it's important to bear in mind that the sparse solver will have to be used, and the FE model will have to be sized accordingly. Femap offers various modeling approaches that can be Femap offers various modeling approaches that can be used to reduce model size without compromising accuracy. It is possible to extract the midplanes of thin-walled solids, which allow you to turn a solid model into a plate model. And Femap also contains some robust beam modeling, if a one-dimensional element topology is more appropriate. Midplane extraction is a powerful tool designed to deal with thin-walled solid models. Such geometries are difficult to model accurately with solid elements without creating huge, unmanageable simulation models, and really lend themselves to being modeled using shell elements. Midplane extraction does just that. The midplanes of the solid walls are extracted and meshed using shell elements, thereby creating a smaller yet more accurate model of the structure. Another important modeling capability in Femap is beam modeling. Femap offers a method of automatically determining the physical properties of a cross-section that you define, and as well as offering a library of commonly used cross-section shapes. Also, as mentioned before, full beam visualization is available, which lets you view the beam elements as if they were solids. Post-analysis, it's also possible to view beam shear force and moment diagrams. The ability to define spatially distributed loading allows more sophisticated and advanced loading specifications to be created that more accurately represent real-world operating environments. Also, it's possible to pick up the results of one type of analysis and apply it to a subsequent for multi-physics problem solving. Advanced tools like this are important, particularly for load and boundary condition definition, as accurate real-world loading definitions are difficult to create and prone to error. A recent addition to Femap's pre-processing functionality are the data surfaces, useful to define more complex loading conditions. Data surfaces come in various topologies, from 1 to 3-dimensional, as well as some special cases. A typical use of data surfaces, shown on the slide, is to take the pressure results from a flow analysis in a pipe system and apply them as input loading on a structural model of the pipes to determine the structural response due to the fluid flowing in the pipes. This is a quote from one of our Femap customers and users, Allseas. This Allseas quote bodes Femap's ability to more easily create an envelope of load cases, which allows Allseas to use the tool more often and more effectively. The more advanced and involved types of solutions invariably demand the ability to modify or enhance the simulation approach. In the process of setting up a model for analysis, there are often repetitive steps of commands that would be laborious to complete without a method of automation. Also important is the need to integrate with third-party software products like Word and Excel. Some competing products offer customization methods which use a proprietary language. A customization capability that uses standard programming languages removes the need for special training and programming abilities. A key feature is the customization functionality, which is seeing increased use within the user community. Femap offers a full application programming interface, or API, with its own non-proprietary programming environment, right inside the user interface. The OLICOM-compliant object-oriented API is a full-featured basic development environment that provides direct access to all Femap objects and functionality. Using the API, Femap can be made to interface with any other OLICOM-compliant program, such as Word or Excel. And you can create custom programs that automate repetitive tasks, search model or results data, or transfer model information to Word or Excel to create another customized report. In addition, many useful programs are delivered with Femap in an ever-expanding library that can be found in the Custom Tools toolbar. As well as the API, Femap also offers a macro capability that allows a series of commands to be recorded, edited and debugged, and played back. One of the simpler forms of knowledge capture in Femap is the Femap Stress Wizard. This is a step-by-step guide through the analysis process, which helps users to set up all of the model attributes in a straightforward manner. With the model set up, the wizard guides the user to solve the analysis using NX Nastran and subsequently review the results. The Stress Wizard can easily be picked up by non-specialists or infrequent Femap users. A simple method of automating work process in Femap is the Femap program file capability. This facility can record sets of commands which can be edited and played back to automate repetitive command sequences. Program files can also be modified to accept user input and executed from API scripts. Femap also has an Application Programming Interface, or API, which can be used to extend Femap functionality and automate work processes. The API is object-oriented and allows direct access to all Femap objects and functionality. It is also OLICOM compliant and can interface with other compliant programs, again, such as Word and Excel. Femap offers a fully featured basic programming environment inside the UI with IntelliSense function descriptor auto-completion and a means of stepping through the program for interactive program debugging. There are a number of pre-written API programs delivered with each release that are accessible through the UI. Now let's take a few minutes to look at a quick demonstration which shows midplane extraction of the solid bracket modeling and subsequent geometry modification in preparation for meshing.
Yvonne?
Yes?
I've got a technical glitch on this side here. I can't do the demos.
All right, not a problem. Let me go back to the...
Sorry about that. I'll get back to you.
Not a problem. Let's go back to the presentation. I just need the screen back. Thank you. In the simulation-driven design white paper, the Aberdeen Group state that customers must develop more products that are more complex for their customers, and they must get them to market on time. The paradox, however, is that more time must be taken in the design process to perform simulation so that time and money savings can be seen in testing. However, Best-in-class manufacturers all use simulation in the design process, which yields fewer prototypes and allows manufacturers to get their products to market earlier and for lower development costs. This is an overview of the Key Knife case study. The challenge that Key Knife faced was to quickly turn innovations into products and diversify their expertise and create new markets. Key Knife adopted Femap with NX Nastran that allowed extensive control over the analysis, leading to replacement of most physical prototypes to virtual prototypes. This resulted in significant savings and reduction in prototype development time for each new product developed, and led to a better ability to compete both in the core business and with diversification into new markets. John Grainer of Key Knife notes that Femap speeds time to market by guiding them with new applications and allowing better control of their mesh, which allows the ability to apply more loads and restraints in ways that make sense. Now let's take a look at how successful Femap is on a global basis. Whether you are a manufacturing company or a job shop, your products or services follow a similar product life cycle. Siemens PLM software helps improve customer responsiveness through accelerated launch, reduced build times, increased profitable growth, extended lifecycle returns, and best practice reuse. According to the Aberdeen Group, migrating to a 3D design solution is not just about designing models. It's also about taking advantage of simulation and analysis tools to assess and validate product performance. Top performers are much more likely to have been pursuing this strategy for more than a year. The Aberdeen Group also related how prototype time and build costs vary across product complexity. This chart here indicates 4 levels of product complexity defined in terms of number of parts and length of development. Products that are virtually tested have a higher chance of passing physical prototype testing the first time. The point here being, get it right the first time. In yet another Aberdeen Group study, through the use of simulation, the best-in-class manufacturers can get highly complex products to market 158 days earlier with $1.9 million in lower productivity development costs. The simpler products are to market 21 days earlier with $12,000 lower product costs. The benefits of using simulation are in manufacturing of products are amazing. So how do we increase customer responsiveness? Through the use of simulation, we can reduce physical prototyping and hence time to market, lower the cost of design, and get a faster return on investment. We can significantly reduce material usage and hence cost, and improve product performance, which reduces product failure in the field and costly recalls. Simulation also feeds innovation by allowing design flexibility and the ability to evaluate different designs digitally. So in summary, Femap is real FEA made easy. Femap has an easy-to-use and intuitive user interface that increases productivity of the engineers that use it. Being easy to use means it's also easy to learn, which brings about a reduced training overhead. Femap incorporates comprehensive modeling functionality that can simulate complex designs. Simulation functionality that is scalable to solve complex engineering problems with a high-quality solution that ensures accurate results. The response to today's question posed at the beginning of this webinar, the Siemens answer is, Femap uses the latest modeling and analysis techniques for efficient and accurate solutions. Improve your customer response by handling more complex customer requirements through the use of simulation, by reducing time to market and meeting their deadlines with reduced physical testing, and by minimizing product costs with more efficient designs through the use of simulation. Before we conclude today's event, I would like to invite you to take a deeper look at Femap. Try Femap with NX Nastran and explore the state-of-the-art modeling functionality of Femap with the powerful analysis capabilities of the industry-leading NX Nastran solver. See how these comprehensive simulation and analysis applications can help you save money and reduce time to market through optimized designs, reduced prototyping and physical testing. In this free offering, you will get access to the full version of Femap with NX Nastran as well as dynamic response and design optimization. There are no restrictions on the number of saves, model sizes, or other factors that would limit your ability to simulate and analyze complete product designs. To speed up the learning process for Femap and NX Nastran, we'll send you valuable how-to tips and tricks as well as links to online training materials. With your registration, we'll also give you access to an exclusive news group where you can share ideas and tips with other analysts. Also, you can see the product in action through some short yet highly informative online demonstrations. Visit the Femap webpage and explore. Thanks for watching, and see you next time